Good afternoon, everyone. Myself Subarna, Senior Research Fellow at the Department of Basic Science and Humanities, Department Bhagalpur. My talk entitled as Bistability in a Predator Prey Model with Crowley-Martin Functional Response. So I will cover this. Predators not only affect the ecology of prey by consuming them directly, but also inflict their behavior and physiology indirectly. At first, Wang et al. Constructed a mathematical model by letting the fear factor, which affects the reproduction of prey population. After that, many studies have been demonstrated that the predator prey systems with fear effect exhibit comparatively more complex dynamics. In further encounters, the residual effects of fear, known as carryover effects, manifest as a sustained alteration in the prey's stress level, foraging behavior, and reproductive strategies. Social communication is an integral part of the life history traits of a population. Some mathematical models have been investigated to explore the role of hunting cooperation in predator prey systems. The additional food sources play a pivotal role for survival of prey as well as predator species. When modeling the impact of additional food sources in predator prey systems, one must account for the generalist predators. Generalist predators means the predators who can eat other food sources except or other than prey species. Harvesting of species is another major issue in a predator prey system, which is very important for the conservation of the resources and also for the social management. So several studies have explored the role of harvesting in ecological system. Another things is environmental factors affecting the survival of species. So consideration of parameters in ecological models as periodic function of time rather than constant would mimic comparatively more realistic situation. That's why in our investigation we assume some model parameters as a periodic function of time. So our main aim of the study are as follows. Firstly, we see how the fear effects, hunting cooperation, additional foods, and harvesting of predators regulate the dynamics of the predator system. Secondly, we investigate how the seasonal influences on model parameters affect the dynamics of ecological systems. And uniquely, we introduce a unique perspective focusing on different periodicities, which offers a valuable insights into the seasonal variations of environmental conditions. So this is our mathematical model. So X denotes density of prey species and Y denotes density of predator species. So here we assume that R is the growth rate of prey population, and due to fear of predation, uh, the birth rate of prey population decreases. That's why you consider Rx divided by 1 plus Fy. So as a Y increases, the birth or growth of prey species decreases, and also you consider carryover effect. That's why we add Cx here and here. So which imply that the in the future encounters between prey and predator species, the less effect will be activated by the predators on prey species. And here we assume D1 is the natural death rate of prey species and D2 is the interspecific death rate. We consume that the we assume that predator population consume prey species through Crowley-Martin functional response, which is described as alpha into xy divided by a1 a2 x plus a3y plus a4 xy. And as we consider that the predator population cooperate each other when they hunting, that's why we add beta y with alpha. That's why when the hunting cooperation rate or the degree of hunting cooperation among predators will increase, the encounter or the rate of predation will increase. That's why we get the modified Crowley-Martin functional response in this form. And also here we assume that the predator population face density dependent death, that is given by this, and a additional food sources will be applied on the predator population. That's why we consider eta 0 as the growth rate of predator population due to the additional food sources. And also, moreover, we consider the harvesting behavior of predators. So Q, this is the Molten type functional responses. So here Q is the catching capability, is the harvesting effort, M1 is the saturation constants. So this is the mathematical model. For the analytical purpose, we assume the initial population size is greater than 0. So these are the biological description of model parameters and the numerical values. Some are uh, taken from previous research published article and some are assumed. So first of all, we find equilibrium points, the population of equilibrium points which always exist. The predator equilibrium point denoted as E1, which is R minus D1 divided by T2. So this equilibrium, that is predator equilibrium, only exists whenever R greater than 0, that is the birth rate of prey is greater than the death rate of prey. Prey free equilibrium denoted as E2 is defined as 0, y2, where y2 is the solution of the cubic equation. So These are the coefficients. So applying the Descartes' rule of sign, we can find the maximum number of positive roots for this polynomial equation, and then we get the defined number of free equilibrium points. So analytically finding positive solution for this equation is difficult, so that we find this through numerical simulation. So that's why we to do this, we plot the polynomial equation in blue curve for different parameter setups. And in the first case, we see that this polynomial equation does not cut with this x-axis. That's why there is no positive solution. And for this parameter setup, we see there exists one positive root for the polynomial equation, and for this setup, there exists two positive solution for the polynomial equation. So in this case, there exists no free equilibrium point. In this case, unique free equilibrium point exists, and in this case, two free equilibrium point exist. Finally, the coexistence equilibrium denoted as E star, where X star and Y star as positive solutions of the following algebraic equation. So, analytically finding the expression of X star and Y star is very difficult. That's why we conduct a numerical simulation to find coexistence equilibrium. And for that, we plot the pre-nullcline and pre-nullcline for different values of R. So, from this, we color this region as for wherever the r greater than 0.15 as d1 equal to 0.15. So whenever r greater than d1, then we can get the non-trivial solution for the pre and pattern alkaline equation. So in this case, we see whenever the range of r is between 0 to 1.5 to 0.3124, there exists no coexistence equilibrium point. And in this region, there exists two coexistence equilibrium point. One is unstable and another is stable. So these two coexistence equilibrium appear through a saddle node bifurcation. And in this region, one coexistence equilibrium disappear through the transcritical bifurcation, and the stable coexistence remains same. And beyond the value of r equal to 0.595, there exists the stable coexistence become unstable. So we get the different values of r for which there exists different number of coexistence equilibrium. So we study the local stability. So the trivial equilibrium always E0 is locally asymptotically stable if this condition holds. Payout equilibrium point will be locally asymptotically stable for these conditions. Under these conditions, the pre-free equilibrium point will be locally asymptotically stable if the following inequalities hold. And the stability of coexistence equilibrium is described by the following equation. So under these different conditions, different situations we will have it. So in such cases, case 1, that if C1 less than 0 and D2, C less than 0 and D greater than 0, then the equilibrium is stable. Moreover, if C square minus 4D greater equal to 0, it is stable node, otherwise it is stable spiral. Whenever D less than 0, the equilibrium E star is saddle point. If both C and D are greater than 0, then the equilibrium is unstable. Moreover, if this discriminant is greater than equal to 0, the equilibrium will be unstable node, otherwise it will be unstable spiral. So the necessary sufficient condition for the existence of bifurcation in the system around the equilibrium point E star are that a critical value of R exists, denoted as R equal to RC, satisfying the following conditions. So under these conditions, the system will have a Hopf bifurcation around the equilibrium E star. So now we draw one parameter bifurcation diagram with respect to R. So through null you describe this behavior. So for lower values of R, that is from R equal to 0.15 to this value, there exists no coexistence equilibrium point, only Pareto equilibrium point exists, which is stable. And in this region D2, two coexistence appear through saddle node bifurcation, one of which is stable, so whose Pareto density is greater, that equilibrium will be stable, and other equilibrium is unstable. And through transcritical bifurcation diagram, this unstable coexistence disappear, and the Pareto equilibrium point become unstable in the region D3. And whenever the system dynamics is observed in D4, the stable coexistence become unstable through supercritical Hopf bifurcation. And in this region, the This rate of equilibrium point is unstable, remain unstable as D3, and the coexistence equilibrium point, a stable limit cycle appear around the coexistence, unstable coexistence. So in each region we draw phase portraits. So you can see there. So this is the rate of equilibrium point, which is globally stable. As from here we can see, there is no interior equilibrium point. That's why it becomes global stable, and therefore we get interior stable, uh, and also this one is stable. One interior stable and another unstable, but the rate of equilibrium point is stable. And here, one interior disappear, and the stable coexistence remains same through transcritical, and rate of equilibrium point become unstable, and this. Similarly, we draw one parameter bifurcation diagram on the variation of predation rate. So for smaller predation rate, there exists two coexistence equilibrium point. One is stable and another unstable, and the rate of equilibrium point become stable. And for intermediate value of predation rate, the unstable coexistence become disappear. Unstable coexistence disappear through transcritical bifurcation, and the rate of equilibrium point become unstable. And in this region, through supercritical half bifurcation, the stable coexistence become unstable, and around which a stable limit cycles appear, and the disease pattern free remains same. Similarly, the phase portraits are drawn, and we also draw bifurcation diagram with respect to beta, and in each region we draw phase portrait. And this is the two parameter bifurcation diagram.